So yeah, so a Feynman-Kac method, you are going to use this method to solve your terminal value problem of the stochastic differential equation. So you are still going to have some sort of a stochastic differential equation, right? So you are going to have some, okay, let's say V11, something, I can say V22, and then they want you to calculate some V, where you're going to have like V of t, it is going to be equals to some function, right? So this is when you are going to use like a Feynman-Kac method, right? So yeah, I can just say that x of t, right? So this is the case where you are going to use like the Feynman-Kac method, because you now have a terminal value problem. So you now have like a terminal value. So you have like you are now going to start from maturity, but then you want to have to find the value at time t, but then you know what that value is in maturity. So this method has like steps, right? So you are going to be given steps to use, right? So yeah, so the number one step that you are going to start with is how to write the associated stochastic differential equation, right? So you are going to write the associated stochastic differential equation, and then you are going to solve it, and then you are going to assume that f is the solution, right? Provided that the function it is given, again that the equation it's a function of f, right? And then you are going to determine it like using, and then you are going to find is differential equation. So you are going to use like ITOS formula, right? So you are going to use ITOS formula, and then you are going to solve it, to solve this ITOS formula using the direct method. So there's no need for you to try to find any other method. Just put the direct method in there, and then you can just leave it as an integral. But what is important is that you would need to find it in this form. And then lastly, you would apply the equation. Actually, you would apply the expectation and then solve for f of t, right? Solve for this part. Solve for this, right? And then you are going to solve for that, right? So, and then, yeah, after you have put that. So this one is often the longest one. So I'm going to look at some past days paper actually, so that we can practice. So you have some kind of a stochastic differential equation, right? Which is a terminal value problem. So there. And then for 5 marks, they say they want you to find the solution of the terminal value problem. So this question is actually going to be 6 marks plus 5 plus 2. I'm not sure how many marks. So it is going to be 13 marks basically to solve the whole thing. So they do take a long time to solve. So what they usually do is that they put them in parts. So they are going to separate them in parts. But then okay, so they are going to put them like into different questions because they take such a long time to solve, right? So I'm just gonna check something on my notes here. Okay, yeah, so they just gonna, yeah. I'm sorry for that. I don't know why it went. Okay, yeah. So the first one is how do you find the associated stochastic differential equation, right? So when you have some differential equation, let's say you have some f I'm not sure if you can see what I'm writing. Oh, there it is. Let's say you have f of 1, and you have some a, f2, then you have some 1 over 2 b squared, and then you're going to have some f22, so f22, then you're going to have some function g. It's fine, I can just say g, right? So to find the associated stochastic differential equation of this, so this would be like d x of s is going to be equals to a d s plus b, right? So b d to the ws, right? So this is how you find the stochastic differential equation. So first of all, you would need to isolate the a and the b. So in this case, they are already isolated. Again, they are already isolated for us. In our case, the a is going to be this whole term, and the b, it is just going to be like the sigma over there. So to find the associated stochastic differential equation, you would simply have like the d x of s is going to be equals to, I assume that a and b are constantes. So I'm just going to have like your a and your b, x of s ds, then you're going to say plus sigma d ws. Is there anyone who would have a question on how this came to be? Again, I do encourage you to unmute your mic if you have any question. But so as you can see, this here, it is. And then you would also need to write like the first part. So you are going to have like x of t. It's going to be equals to x, right? So you are going to integrate from t to u. So is there anyone who has any question on why, again, on how to write the associated stochastic differential equation? And by the way, I can read your question on the on my PC. I do have like 2 things. So if you don't want to unmute, you can always write your question down. And then they ask you to solve it. So again, I'm not gonna do anything related to like to solving the stochastic differential equation because I hope this question doesn't have an error as well. So I'm not gonna do any question related to how to solve the stochastic differential equation because I assume that you can, because I think there's only one person who asked about the stochastic differential equation. Fuck. Oh my God. Yeah, I'm sorry for that. My screen just switched off. Uh, So yeah, as I was saying, the associated stochastic differential equation, you can find it and then you can solve it, right? And then the solution to the stochastic differential equation, it is just going to be your x, sorry. But yeah, so now once you have this solution, now we go to the parts that we need to do, right? So part number 2, 3, and 4. So how do you do the, okay, how do you do the remaining parts? So 1, so we have, again, we can find the associated stochastic differential equation, and then we can solve it. So now, how do you do the next 2 parts? Again, like the last 3 parts. So now you are going to assume that F is going to be a solution, right? So in the test, you need to write this part, right? So it is going to be the solution of the term, of the terminal value problem. And this solution needs to be continuous. It needs to be also, it also needs to be like differentiable, right? So you need to write this part so that you can have marks. In the test, you would not have this, so you would not have the 4 steps written down for you. But then you would be expected to remember them by heart. So you are going to, first of all, write that F is a solution of the terminal value problem, and that it is continuous, and also it is differentiable. So after you wrote that part, I think they can give you like half a mark. So after you have written that part, you need to find the differential equation of that solution, right? So after, so since you already say that F is going to be a solution, so F is going to be a solution. So F is going to be a function of X. I'm just gonna discuss, right? So you already know that F is a solution, right? So it means that the stochastic differential equation D of F of T, X of S, using Ito's formula, it is going to be the first derivative of F. So you are going to have like F1, ds, right? And then you are going to have like F prime 2 d X of S. Then you are going to have like 1 over 2 F2 so F prime 2. So D of X of S squared, right? So we already know what your X of S is, right? So what you need to do now is to just substitute those values. So you do know that your F1 ds, then you're gonna say plus F2, right? So F2 D of X, you already saw, again, you already found the associated stochastic differential equation. And that would have been your A, B minus X, D, ds plus sigma, D, WS, then plus 1 over 2. So the F prime prime, we're gonna have like F prime 2. And then the ds times ds is 0, and the ds times dws is also 0. So you are going to have like your c sigma squared again ds. So when you are going to simplify this, you can isolate them, right? So this, okay, maybe just say this, um this and this are like terms. So you can just write them, you can put them together. So you would have f prime 1 plus a b minus x, f prime 2 plus 1/2. So you're gonna have like this, you're gonna have squared f prime 2 everything ds plus sigma f prime 2 d ws. So I know that you have a, okay, so some of you might even have a memo. So the memo did make a mistake, okay, on the last part, uh, on this part over here. So yeah, again, so don't be confused on that one. It was a simple mistake, but a mistake nevertheless. So, and then since you already have, so since you can already see that I don't know which color can use. Since you can see that this part, that this part is the same as this part over here. You are able to just write the equation part of that. So you are able to just say minus RF instead. So you can take the RF to the other side. Is there any question on what I just said now? I can see that sometimes the pen takes time to reflect on your pieces, but I hope it doesn't affect too much. So you're gonna have like minus f minus RF, sorry, ds plus c sigma f prime 2 dws. So this is how you write it. So this is going to be your differential equation. And then for step number 3, you need to then so since you have like, so since now you now have like so since now you have like your d f of s to the w of s is going to be plus to minus now f s to the w of s ds plus f prime 2 d to the w of s, right? So you can just use, so I say that you can use like a direct integral over here. So you can just integrate it directly. So you are going to say the integral from time t to u of d f of s. So it's going to be the integral from time t to u of, it is not negative because the negative would go to the other side. So it is not going to be negative because the negative is going to go to the other side. And like the whole term is going to go to the other side and then it will become a positive. And you would have like r f s w f s ds plus integration from t to u of c sigma f prime 2 d to the ws. Right? And then you are going to, okay, so this is the easy part, right? So to find your solution here, you just have like f of u, that is f, okay, x is a function of f is a function of, switch. Yeah, so as you can see here, it's x instead. Here it's x as well. So you will have like x, you will have x. I don't know how I, you know, how I missed that. So yeah, so you should take that. Can when I went to the next page, I forgot to clear out the notation. So f of x of u, so you're gonna have u, so u minus f of t, x of t. So and then we say that x of t is just going to be x of, okay, so x of t is just gonna be x, just gonna be your x. You just have your x, and then you are going to then yeah, and then you can just leave the left hand side as it is, right? So you're just gonna have like the left hand side as it is. So ft u r f s x of s ds plus integral from t to u f prime of 2 t x of s d to ws. So yeah, so is there any questions so far? I can see there's someone who's asking a question, but I can't see. Yes, it was positive. I just forgot to move it to the other side. I'm gonna, and then how about Kara? Are you still fine? Kara Mininza. Okay, I'm not sure if she can hear me. And then how about you? I mean, I hope my mic is not off. It's not off. Okay. It's a silent crowd, but I'm not surprised because there's like quite a number of you. Anyway. So yeah. So so you do need to take the notation as they are, like when you are going to go down on your equation. So as you can see, I did make a mistake over here, like on top. Hence I'm like, hence someone, I just forgot their name, say that it is indeed positive. So you do need to take it to the other side, and f is a function of x, not w. So okay, so we're gonna go to the next step in that case. Okay, if there's no question. So now the next step is, how do you find the expectation? So this is usually so this is usually the hardest part. So in the next step, to find the solution for this one, to find the expectation, you would apply the expectation on both the left hand side and the right hand side. So you would have the expectation of f u x of u, right? And then you will also have the expectation on the on that one, but then that one, it is currently where we are, so there is no need for you to write it as an expectation, because whatever it is because that's where we are. So so there is no expectation, so it is basically a constant. So you are going to have like f t x, and then you are going to have again equals to, then the expectation of that with respect to s x. So there is no x there, so you can just put the expectation of the integral from t to u of r f of s x ds, and then plus the expectation of the integral from t to u of sigma f mt2 x of s d to w of t. So, and then you can simplify this then. So there's the step after the simplification is what I need to get to. So you would have the expectation of fu x of u minus f of t x is going to be equals to the integral from t to u of the expectation of f s x of s ds plus 0. So plus 0. So because the expectation of of the differential equation would be 0. So they would actually give you that part. So they would actually give you that under, again, I'm like on the first page, like under like formulas and result. So this, again, so this part would be 0. So there's no need for you to focus on it. So now this is where the magic happens, right? So you are going to let this expectation, you are going to let g of u be equals to, or maybe I can say that to make it more correct, you are going to let the expectation of f of u, x of u, be equals to g of u. So if this is the case, so the last equation can be written as g of u minus g of t. I prefer to just write it as f of t. So there's someone who wants to join. So f of t of x yeah, so I'm just rewriting this as g, right? So f of t, we're going to have t over the x actually. So you would have like your x, and you would have the integral from t to u of r times your g of s ds. So you are going to differentiate with respect to u. So you are going to find d u, right? So you are going to differentiate with respect to u, right? So d of g of u, it is going to be, so this one is going to be 0 equals to, so when you are going to find the derivative with respect to u, so you can just use like the fundamental theorem of calculus to find the solution. So you would have like g of u s. So to make it easier, so you can just say that g prime of u, and then you know that g prime of u, that this part, the g prime of u can be written, so the g prime of u can be written as like d g of u over d of u, right? So you can try to solve this part. So you are going to have like the d g of u over the d of u equals to r g of u, and then you're gonna solve it. So this one, I'm sure most of you already can see where is it going. If you want to just change this thing to s, right? So you can just change this thing to s, so that you can have the integral from time t to u. So, and then you would just have like g of u is going to be equals to g of t e r u minus t. So this would be your solution. Is there any question on how to find this solution? And then from here on, you are going to substitute this back into the equation. So you remember that the equation was actually g of u minus f t of x. is going to be equals to the integral from t to u of r g of s d of s. Now you are just going to substitute that value in there. The g of u back into the equation. So what you would get is that you would get like g of t e r u minus t minus f of t of x. And then you would have the integral from t to u of r g of t e r u minus t ds. I mean like s actually. So s minus t. And then when you are going to integrate that, you would have your g of t, and then you would have the integral from, and then you would have your e r s minus t going from t to u. And then the last two parts, okay, kind of like the first part, the terminal point is going to cancel the other terminal point. So what you would have is you would end up having like f of t of x is going to be equals to g of t e r. And then you're going to have t minus t. So basically, so t minus t is just going to be e to the power 0. So this would just be like f of t is going to be equals to g of t. Is there any questions on how this came to be? So you are going again. So again, so you have assumed that g of t, I mean like g of u is the expectation of f of u, x of u, right? And then you also know that g of t, I'm like g of u is going to be g of t. I think it was e r u minus this, right? So when you are going to make g the subject of the formula, so g of t, it is going to be equals to g of u e minus r u minus t, right? So you are just going to substitute this back then. Yes, you can just substitute it back there. So you are going to have that g of t, taking that f is just going to be f. This is going to be equals to this. You would say that is equals to e minus r u minus t. Since g of u is the expression of f, you can just say here that it's going to be the expectation of f of u x of u. So yeah, this is how you can find your solution of the terminal value problem. So yeah. So I will try to find the people who voted for this one to ask if they are satisfied. Maybe I can start with Tinyeko. Are you still fine, like Tinyeko? Okay, so do you have any questions? Like, do you want me to re-explain something? Yeah, but some Kelesiwe. Are you fine with? Did you understand? And
yeah, okay.
Okay. All right. And don't be scared to ask me questions, because I can explain this again. So yeah, so that was the terminal value problem. I don't know if there's, I mean, like the Feynman-Kac, like using the terminal value problem. Right. So yeah. So I think maybe we can just continue from here. So I'm sorry that these chapters, they are basically like computation. There's not much theory. So there's not much for me to say, but to just show you the steps. Unfortunately, so this is what I have to do. I just need to show you the steps on how to solve it. So there's not much to explain or to give you theory on. So because there's nothing much happening here. So, but then I do want you guys to understand before you leave this session. So there's no point of me rushing over everything. I would rather stick to one topic so that everyone understand. Because last time I think I did like, again, I tried to do everything and then we ended up not understanding, like few people actually understood. So yeah, I can't rush over anything if you guys don't understand. But since that there's no question, I'll just move on. So the next topic that I wrote down. I think I wrote that paper. I think this is Feynman-Kac. That's the Black-Scholes partial differential equation. Yes. So we are not going to derive the Black-Scholes partial differential equation, but then we are going to talk about. I don't know why I closed it. Okay, well, it's lost. So yeah, under the Black-Scholes partial differential equation. So the Black-Scholes partial differential equation, again, it's a differential equation. So the Black-Scholes partial differential equation is an equation that we are going to use to price our continued claim. So the claim can be a put, it can be a call, it can even be futures market. So it can even be like a future, but we don't do futures here. We do options like call and put and some combination of call and put, some sort of exotic or anything. So kind of options. Right. So, but then the Black-Scholes partial differential equation can be written in this way. It can be written in this way. So you are going to have like f prime 1, then you're gonna have like plus r. The r being the bank rate or the risk rate. Then you're gonna have like your x. Your x would replace like the value of the share at each point. So v prime 2 plus 1 over 2 sigma squared x squared. And the sigma is going to be like the variance of the share. This f prime to 2 minus equals to r v equals to 0. And then you are also going to have a terminal condition that v of t of x is going to be equals to some function of x. Actually, here I can just say that x of t if I want, but it's just going to be x, so it's fine. So this is known as the Black-Scholes partial differential equation. Right, so this is known as the Black-Scholes partial differential equation. So, so previously we saw that okay, under this Black-Scholes partial differential equation, there are a few things that you can take from here, that you are able to find the associated stochastic differential equation. Stochastic differential equation. And that differential equation, dx of s, was going to be equals to, I don't see where the d went. So d of x of s is going to be equals to r x of s ds plus sigma x of s d to the ws, right? So this was how you find the associated stochastic differential equation. And then you can either use like the matching of coefficient, or you can use the judicial substitution to solve it. When you solve it, the solution for this one, x of u, is going to be equals to x. So this, say that x of t is going to be equals to x. So x of this is going to be this. It's going to have r 1 over 2 sigma squared u minus t plus sigma to w u minus to wt. So this would be the solution to that, again, to that associated stochastic differential equation, right? And then the solution to the terminal value problem, right? So the solution to the terminal value problem of the terminal value problem, right? So you can use like Feynman-Kac method, right? So when you are going to solve it, you are going to find that v of t of x, in this case, I can just say s, right? So of x is going to be equals to, you would have like e minus r t minus t, and then you would have like the expectation of v cap t as t, right? So this is, I'm like, this would be the solution, like using the Feynman-Kac method. So yeah, so as you can see, now we are going to apply what we have learned like previously on the Feynman-Kac method. I mean, like on the, on the Black-Scholes partial differential equation. So everything that we have learned under the stochastic differential equation, actually all the way from Brownian motion. So on how to find like the Brownian motion, on how to standardize it, on how to find its differential equation using like the Riemann sum, how to write it as an I2, how to solve the initial value problem, how to solve the terminal value problem. All that have led to this point on how to solve the Black-Scholes partial differential equation. It's just that we need this skill. It's just that we need that skill. That's why they do like a lot of example, like a lot of other questions. But what we mostly wanted is to solve the Black-Scholes partial differential equation. So at this point, we can be fairly sure that we can solve it all the way to this point, right? So that being said, the other thing that we will be concerned about now is the terminal condition, right? So how do you find the terminal condition? So the terminal condition, so that v of t, s of t, right? So this terminal condition that they just put some psi there. So now we want to find that solution. So now we want to find the solution of the terminal condition, right? So let's say perhaps now that the terminal condition is a call. They normally solve for the call, and then they would separate them into a cash or nothing as well as the share or nothing, right? And then they would solve them independently, right? Sometimes they can solve for the put, but if you have the call, you can just use again, there is a method that you've learned in chapter, like in the first chapter, where so it's called the put call parity. So you can just use that one. But either way, I think I will just, okay, so which option do you guys want me to solve actually? Let's say I have S of t. Which one do you want me to solve? The call, the put, some cash or nothing, or some share or nothing? Again, I can say call or put. Which one should I focus on so that we can be more clear? There's also some other ones, some exotic one. Exotic, but we need to stick to the easy ones. Okay, see, again, I think I get share or nothing. So it's cash or nothing. Cash or nothing is the easiest of them all. Then there's asset or nothing. So the asset or nothing is the share or nothing, basically. Okay, so I think I can do the call, because the call option combine both cash or nothing. Right. So yeah, I mean, like, yeah, so we're gonna have that part. So we need to know how to derive it, right? So we know that we already say that the solution to this that v, or this thing, is just gonna be some call, right? So I'm gonna say I'm gonna focus on the, on that expectation form. I'm gonna focus on the expectation. So you're gonna have like the expectation of some psi of the share. So the share, by the way, is gonna be like x e r minus 1/2 sigma squared t minus t, right? We're gonna say plus sigma. Is it sigma? Yeah, if it is sigma, WT minus W this, right? So what you need to remember is that under Wiener process, I'm like under the standardized Brownian, under the Brownian motions, that WT minus W small t had a normal distribution with mean zero. It always had a mean of zero, and the variance would be the distance, right? So it would be like t minus t, right? So when you wanna normalize this, so when you're gonna have like this minus W small t over the square root of the variance, this would be a standard normal distribution, right? So it simply means that if you want, you can just let this thing equals to y. In that case, the expectation of that, so the expectation of this sign, it is just going to be some value, this whole thing over here, okay, we can just call it m. It is going to be x e m plus, and then we can just say sigma, the square root of t minus t times y, where y is going to be your standardized Brownian motion. So basically, this is going to be like the integral from negative infinity to negative infinity of your psi of x e m plus sigma, this is square root of t minus t y, and then you would say times the function of y times f of y dy. So this is what needs to happen. So this is what you will need to solve. Maybe I need to write it down nicely. You would have the expectation of psi of s of t. This is going to be the integral of psi of xe plus sigma t minus t y f of y dy. So this is what we need to solve, right? So now suppose that psi of s of t is a call. So if it's a call, it means that you are going to find the maximum between if it's a call between the share, so it's going to be st minus k or 0. So if you remember, this would be the call, right? If you want to just say that st minus k when st is greater than k, or 0 when st is going to be less than k. This was the payout for the call. If you remember how to draw it, so if you know how to draw the price in the payout for the call, it is going to be something like this. It is going to be something like this. It is going to be something like this. So this is how this payout look like. So now you would need to solve for this, right? So I'm not sure if you guys can see. Can you guys see? Or can you just see the okay, there it is. Yeah, so this is what we would need to solve, right? So if you are going to solve for this, so you are going to basically have like two integrands, right? So the first part would be 0, and then the other part would be the part which is greater than 0. There's someone who wants to join. Okay, welcome. Anyway, so yeah, as I was saying, So you are going to have like two integrands because you are trying to integrate on both sides, right? So you are going to integrate the part which is going to be equals to 0 and the part which is going to be greater than 0, right? So, and remember that ST has to be greater than K. So you need to write this thing in terms of 1. So you are going to have, I can just call this thing the whole I. I can just call this one the whole I. This would be like your I, right? So you are going to have like your I, which is going to be equals to the expectation of psi S of t, right? So you are going to basically have like the integration from negative infinity to some point that you don't know about, right? Times 0, y, again, f of y dy. And then you are going to have the other part where you are going to integrate from some part you don't know all the way to infinity, right? Of the of st minus k. And then you're going to say f of y dy. So how do you find those parts that you don't know, right? So st has to be greater than k. So st is greater than k. So st is greater than k. But then we also know what is st. So st is going to be s. If you want to just say x. So st is just going to be x e r minus 1 over 2 sigma squared. T minus small t. And then you're going to say plus sigma dwt, and then this, right? Then this would be greater than k. But if this is going to be greater than k, but remember that actually this one you had to write it as y, right? So you will have like the square root of t minus small t times 1. In that case, your y is going to be equals to the ln of k over x. And then this whole part, and again, you should remember that this part was your m. So minus m over sigma square root of t minus t. So yeah, this would be
Oh, sorry, what's in front of f of y?
f of y is the y.
Oh, sigma.
Which f of y?
Okay, the orange is the first part of the integral from negative infinity to the block.
Oh, okay,
What's
yeah.
the integrand?
It is still y. So again, I'm not sure if I understand your question. So, oh, it's 0. So you have 0. So you have 0 f of y because you have two parts under. So under the call, again, so I'm not sure if you can see my screen moving. So I have two screens. The other one is moving slow, but from my side, I can see what is happening. But did you get the part when I said the RSY? I'm
Okay,
like,
it's clear now. Thank you.
oh, okay, thank you. I think that would have, okay. I should stop guessing the names, it's fine. So yeah, so this would be your y, right? So your y is going to be greater than that, right? So you are basically going to say your I is going to be equals to the integral from, you can just call this part A, from A all the way to infinity of st minus k. And then you're gonna have like your f of y dy, right? So y is a standard normal is a standard normal distribution. So from here on, what you would need to do is separate them. So now what you need to do is to separate them. So you are going to have like the integral from a to infinity of S of t, f of y, this minus the integral from a to infinity of k f of y dy. So as you can see, this would be like your share or nothing basically, and this would be like your cash or nothing, share or nothing, or asset or nothing. So when you are going to, again, you can do this one, and then you can do this again, this part as well. So I'm not sure if you guys want me to go into details about these two things. Joshua. So do you guys want me to finish up these two things? You can call this one, you can call this one I1, this one I2, and then you can solve them independently. You can integrate them independently. So which one is a little bit difficult? Maybe I can do the I1. So I'm gonna do the I1. So I'm gonna focus on the I1. So I1 is going to be equals to the integral from a to infinity of S of t. Oops. Okay, can you still hear me? I can. Oh, it's just my screen which is, it's just my screen which switched off. I thought maybe it locked out again. Okay, yeah, so I was saying that you can then integrate I1 and I2 separately. So ST, we say that ST is going to be equals to what? ST is going to be equals to, I should use a block time. You're going to integrate from a to infinity. ST was your x, you can just say x, e, r. Actually, there's no need to write that. You can just say m plus your sigma square root of t minus small t y. And then your f of y is your standard normal distribution, right? So you're gonna have like your 1/2, just say like your 1 over square root of 2 pi. And the variance is 1e minus 1 over, yeah, it is 1/2 y squared dy. And then you can put these things together. You're gonna have like the integral from a infinity of x e to power m, right? And then you're gonna say 1 over the square root of 2 pi. And then you can say a like sigma t minus small t, and then minus 1/2. Actually, if you want to just say like, you can just take the minus 1/2 outside. So minus 1/2 y squared minus 2 sigma t minus small t times y, this dy. And now you are going to use like completeness of the square, if you remember it from high school, to then write this thing as a square. So you are going to have equals to x e m integral from a to infinity, right? So plus 1 over 2 pi. So you're gonna have like 1 over 2 y times that. So again, it is going to be twice. So 1 over 2, you're gonna have like y minus sigma square root of t times t. So you're gonna have like t minus this, everything squared, and then that is going to also be minus like 1 over 2. I know that you would have something, you would have like, again, they are going to square, so you can have like C sigma square T minus T. So I have no idea what I'm talking about. So you would have squared T T, I don't know why it's not writing, T minus T. I think the 1 over 2 would still be there. So times 1 over 2. Yes. Am I right? No? I'm just trying to be quick. Yes, I think that will be fine. Yes. And then from there on, dy. Again, you can just take that one outside as well. So you will just have like your x, your e, m minus 1 over 2, C sigma squared, T minus mod T. And then you would have, and then you can again, and then you would have this 1 over 2, the square root of this pi, e minus 1 over 2 y minus the mean everything squared dy. So if this is the case, you can try to standardize this again, right? So where you have your y, where you have your a, you can just put again. So this is the again. So the a is with respect to the y angle. So you are going to differentiate your y. So your y is going to be minus C sigma the square root of cap T minus T. So so you can just let this be equals to Z. And then you're gonna make this differentiation with respect to Z. So you would have like dz is going to be equals to dy. So you would basically have like your x, your m minus 1 over 2 C sigma squared. The square root, oh no, it's not the square root. T minus T. And then you would have the integral from your a minus your sigma, the square root of T minus T to infinity of like 1 over 2, 1 over square root of 2 pi e minus 1 over 2 dz squared. And then, yeah, this would be it. So you would have like your x e m minus 1 over 2 C sigma squared T minus T. And then you would have like your standard normal distribution, the cumulative distribution of your A minus this minus this. So this, again, so this would be your solution of the first part. Do you guys have any questions? Any questions? I can read your questions by the way. I think I had Rutendo's was who asked me a question. Rutendo, are you satisfied yourself?
I'm okay, thank you.
Okay. And then Laboranis, are you fine? I'm just trying to check on my notes. Okay, I don't think that will just anyway. Okay. Read to meet. I know you. Exactly. Are you also, again, are you also satisfied? I hope you guys like, okay. All right, great. So yeah. And then the,
Sorry.
yes,
In the cumulative thingy,
yes.
should it not be the negative of that value since it's from a value to infinity instead of negative infinity to that value?
Yes, actually. So you are going to have the negative of that because you are moving from the from the negative to the other side. So what I could have done is to say 1 minus, but yes, you are basically going to have like negative of that. So you can always have like a positive to and then negative to the other side. Was I doing a call? Okay. Yes, so yes, you are correct. This is how it should be. So I don't think I've solved this thing before, but yeah, you are right. I think it was Ria who asked me the question. Okay, because the standard normal, because again, the standard normal would have to go from negative infinity to some point there. So since this is a standard normal, and it is around 0, where the mean is 0, then you can just swap the signs. Yes. Again, I don't think I would do the other part as well. Which other part is it? Some other part. I just forgot. I2. Yeah, but then unless if you guys want me to do I2. I have no idea where I put my paper. I put these things in order, but I messed up. Okay, there. Okay, so now we were on Black-Scholes equation. So we can go to the hedging and the group. So before we go to the hedging and the group, do you guys have any questions so far? I can see there's still like a lot of page left. Maybe I do have some question. No, nothing. Okay, so the Greeks basically just tells you the rate of change of what? So the rate of change of your contingent claim with respect to a certain parameter, right? So you would have some, again, I can say that, let's say that you have a call, right? So a call is going to be like C of T, S of T, right? So if you have a call and then you find the derivative of this call with respect to, okay, let's say a share, right? So the derivative of the call with respect to the share, this would be known as delta. So this delta is a Greek. So when they tell you about the Greeks, just know that it is the derivative with respect to a certain parameter, right? So it tells you how for each unit of the parameter, the value of your claim would change. So this claim can be anything. So I just used like a call in my case to describe what this parameter is. So again, so I just wanted to give you that introduction, but then I am going to talk about them in detail. So the first trick that you are going to learn is the delta. So this would be the first trick. So the delta, right? So delta basically tells you the derivative with respect to the share price of, I can just say that V. So V is your contingent claim. So V is your contingent claim, right? So you are going to find the derivative of this, again, of this claim with respect to the share price. So this basically tells you that if the value of the share price increases by one share price, I can say that by R1, then what's going to happen to the value of the claim? Let's say that maybe perhaps the delta of a claim, it is going to be 5. It means that if the value of the share price increases by R1, the value of the call would increase by R5. If it's negative, it means that if the value of the share price increases by R1, then the value of the claim would decrease by R5. But so, yeah. So this is what this is what the delta tells you. It tells you for every unit increment of the value of the parameter. In this case, the value of the parameter is the share price. For every increment of the value of the parameter, how does the value of the claim changes? Right. So you can find like the delta of the call. In this case, you can just say that the delta of the call is just going to be like S of t, C t as of t. It tells you for every unit increment of the call, like of the share, what's going to happen to the value of the call. This is what the delta basically just tells you. I hope that makes sense. We also have another Greek, right? So called the gamma. So the gamma is the derivative with respect to the share price, but then of the call. So basically this is going to be like the second derivative with respect to the share price of your claim. I used V for the claim. Right. So this one tells you the rate of change of the call. Again, I'm like of the delta. Right. So for each increment of the share price, so what's gonna happen to the sensitivity of the delta? So how does the delta change? So this is what like gamma tells you. So it tells you like the second derivative of the claim. Or you can say that it tells you there's the sensitivity of the call. You can again like the sensitivity of the delta to the share price. Is there any questions? Maybe, but I don't see any questions, any messages. No? And then the other delta, I'm like Greek, is called the vega. So the vega is with respect to the volatility. So this one, it measures the sensitivity of the claim with respect to the volatility of the share price. Okay, yeah, the volatility of the share price. Right. So for every increment of the of CC sigma, what's gonna happen to the value of the call? So again, this is what they basically tells you. So yeah. Am I being too fast? Or do I need to go into details? I can go into details if we have to. Yeah. So this is what Vega tells me. Do you guys want me to go into details? I can go into details if I have to. And then there's also rule. How do you write rule? That's fine. Okay, so there's rule. I think this would be rule. Nah, this is, I think, yeah, okay, sharp. This is rule. I didn't cram how they look like, but yeah. Again, so the one for rule, so the delta for rule, you would have that it is going to be like the derivative with respect to the share, again, I'm like to the risk-free rate, right? So this is what the rule tells you. So it tells you how sensitive the value of the claim is to the changes of the interest rate of the bond or of the bank. So basically, the higher the value of the Greek, the more sensitive that claim is to the call, like to the specific parameter, right? So it means that if your Greek is higher, right, for could you please repeat for Vega? Which one is Vega? This one is Vega. So yeah, so the one for Vega, so this one tells you like the sensitivity of the claim with respect to with respect to the volatility, meaning that if you are going to have a claim, let's say maybe you have a call, right? So a call, right? And then you'll find that the vega for this call is some value, right? So here is some value, right? It is 1, or maybe let me say 2. It means that if the volatility of the share price increases by 1%, then the value of the call is going to increase by 2%, right? So the higher this value of the vega is, it means that if the volatility of the share increases, it means that if you are going to add an asset that is very volatile, then it makes your whole call as well. So the whole call option to be volatile as well. So this is what happens when you are talking about like the kinks. So in this case, we are talking about the vega. So it basically tells you how sensitive is this claim. In our case, our claim is going to be a call, right? So it tells you how sensitive is this call to the parameter sigma, which is the volatility of the share. So if the vega is very high, it means that this asset is very sensitive to the share price. Again, to the volatility of the share price. So yeah, it helps you understand how which asset to invest in, which one to hedge, how to hedge them, and all those kind of things. Not every risky asset has to be avoided. I do think this is how you write rule. I hope this is how you write rule. And then the last one is theta. So theta tells you the sensitivity with respect to time. We all know theta. So it's going to be the sensitivity with respect to time of the claim. So over time, what's going to happen to the value of your claim? If you are going to hold this contingent claim for a year, how would it change? Is it going to increase or is it going to decrease? So this is what theta tells you. So it tells you like what's going to happen over time. So how sensitive is your asset with respect to time? Let's say perhaps we have a put, right? And then you'll find that the theta for a put is 0. It means that given other parameter being constant, so over time, the value of your put is not going to change depending on time. But then let's say that maybe you have a call, right? And the theta for this call is going to be like 5. It means that over time, I can say that after a year of holding this call, its value is going to increase by 5 francs. If it's negative, it means that as time goes on, the value of the call is going to decrease in value. So the longer you hold it, the more it loses value. Yes. So yeah. So I hope this things make sense now. So now the only thing that would be that we would need to do is to how do you derive them and how do you hedge? So there is a result which I wrote down. This is the Blackshaw. This is the hedging. So there's a result that that you need to know. They would write it in the same as the test. That S. By the way, there's a difference, right? So if I'm going to write this, if I'm going to write this means like cumulative again I'm like cumulative standard normal distribution, right? If it's like this, it means that it's just like the standard normal distribution, like it is not cumulative, right? So yeah, you should keep that in mind. So if you have like your ST, this D1, it's gonna be equals to T this minus this D2. So this result would almost always be given to you. There is a proof for it, but I've never seen it asked at all. So, and in most of the tests that I looked at, you would always be given this equation, but I would advise you to cram it if you have to. And then if you don't know how to cram it, you can ask me for the proof. I can send you the the proof. Actually, I don't have it, but I can do it. Yeah. So yeah. So but it is there in a same semester test, but sometimes I don't see it. Maybe they put the formula sheet say at least, so I'm not sure. But this is a very important proof. I mean, like results that you need to know. So be that as it may, which one do you can, I think a call, that's fine. Let's say that you have a call. A call has this value, ST, the standard normal, D1 minus KE minus R T minus T, standard normal D2. Yes. Okay. So perhaps you have this equation over here, right? Of a call, and they ask you to find one of the Greeks. So which Greek do you guys want us to look at? By the way, so to avoid confusion, I would write down, so D1 is going to be R plus another 2 sigma squared T minus T lim of ST over X over K. So over something over sigma square root of T minus T. So so this would be your D1, and then your D2 is just going to be like D1 minus sigma T minus T. I think that's it. Yes. And then you can just simplify it further. So yeah. So if you have D1, you have D2. So which Greek do you guys want us to prove? So we have delta, we have gamma. Which one else? Is it the vega? The vega is the volatility one. I think I can just say this one is the rule. And we also have the theta. So which guys, which one or which ones do you want me to show you guys? Maybe I can ask Rhea. And Muniwa. What have it? So you can unmute your mic and then you can tell me which one you want. Gamma. Okay, so with the gamma, it means that we need to find the delta. And then Amin, I'm not sure if I'm saying your name correctly. Arman. Arman. Arman, which one do you want me to look at? So someone says like this. To find this, we need this. Okay, so I guess Ghost is my only participant. Okay. Okay, maybe level one. Yeah. While you guys are answering, I think I'll just find the delta one. Okay, and also for which option, call or put. But I would always advise you to look at for the call, and then you can use the put call parity to find for the put. That would be my advice, but I'm gonna look at the delta. So delta is with respect to the share price. So the first derivative with respect to the share price of the call. So this would be, so as you can see, this first part, right? You have ST, and the D1 also have your ST. So D1 is a function of ST. So you would need to use chain rule. So here you don't have ST, but D2 does have ST. So you would say that, so here you are going to find the first derivative. You are going to kind of like of ST, and then you're gonna leave the standard normal as it is. So the first derivative of ST with respect to ST is just going to be 1. So you would have like this D1 plus ST, and then you would have and then you would have to standardize again. I'm like, you would have to derivative this one, and then you would just have like the one which is not accumulative, and then you would need to derive like D1. So D s of T D1, and then you would have minus K E minus R T minus this, and then you would have this D2, then you would like derive this with respect to D2. So basically what you would have now is something. So you would have like this D1, and then the remaining ones, so you would have like can I say that s of T D1 minus K E minus R T minus this D2 times the derivative of that one. They are going to be the same. Because of the lien, right? So then you're gonna have plus this D1. So we say that when you use that first part, this thing is going to be equals to 0 because they are equal. So this is by result. So you just have like this one. I think this is all that you'd have. but I just need to confirm. Is there any question so far? The result is that ST2. Yes. Is there any question? Ghost. Okay, I don't know your real name, but are you fine so far? Should I cancel it and show you again? Okay, I assume that you're fine. And then for the other one, for the second derivative, so you are going to say this is going to be like your delta. How do you write delta? Yeah, it is. So this would be your delta. So your gamma. So gamma is going to be the derivative with ST of the delta of the cone. So you would have the standard normal d1 times the derivative with respect to ST of d1. So, and then you would have like this d1. And remember that the ST is on the line. So, and the line is ST over K, right? So you would basically have like this ST over line of ST over K, right? And then you would place that, and then you would just have like this d1. And then you would have 1 over ST over K. And then you're gonna derivate. No, there's the ST over K. That's gonna be this. The square root of T minus T. And then you would have like 1 over K. And you would have 1 over K sigma the square root of T minus T. And then you would basically have like this D1 over ST K sigma T minus T. Is it fine, Ghost? This is T, it's not plus. I hope so. And if you can write, you can just react. It's fine. I just need to confirm on the graphs. Yes, it is. Okay, so since no one else have mentioned any other Greek, I would assume that you can do the remaining Greeks, right? So I'm gonna go to hedging now. I'm gonna go to hedging. And then we're gonna stop after here. So hedging is about like adding portfolios together so that you can counter against Okay, I think the screen shut off, but yeah, I'm back now. So hedging is when you are going to add like assets together so that you can counter against the sensitivity of that gain of that financial derivative, right? So you are basically going to add some assets so that you would reduce what take away the risk that you have against the sensitivity, right? So sometimes you will need to add more shares or less, or less shares, or take, or short sell some shares so that you wouldn't be exposed to the sensitivity of the parameter of the share, right? Yeah. So basically, you are going to build a portfolio. So you are going to have some portfolio, and then in this portfolio, you are going to say that you have bought some calls, let's say maybe some number of calls, A number of calls, and then you have like B number of puts, and then you would need to buy some C number of shares, right? So this is like how you can count the number of your assets here. Né? So when you want to hedge, so you basically just need to like find ways in which you can reduce the sensitivity. So again, I'm going to do some question over here. I have already done this one, so I just need to consider it. So now suppose that, so assume that the share price of ABC stock is 20 Rand and the risk-free annual interest rate is like 0.5 and the volatility is this. How many shares are needed to make your portfolio delta neutral in the following case, right? So you have sold 1,000 calls and the strike price is 25. So you want to know how many shares do you need to buy? So what needs to happen here is that you would say that to make it delta, how many shares are needed to make your portfolio? So you are going to have some portfolio, right? So in this portfolio, you have sold, so minus 1,000. So you have sold minus 1,000 calls. So you want to know how many shares do you need? So how many, okay, so the alpha counts how many shares you need, right? So if this is the case, you want to make this, you want to make this portfolio delta neutral. So you want DST of your portfolio to be equals to 0, right? So you don't, okay, like you don't want it to be sensitive to the share price. In that case, you are going to apply the derivative on both sides. So ds of t of pi is going to be equals to minus 1,000. And then you are going to have like the delta of the call plus alpha. So the derivative of the share with respect to the share price is just ST. So, and this thing has to be delta neutral. So you are going to have 0. So you would have like minus 1,000 delta CT plus alpha. So basically alpha is going to be 1,000 delta CT. So we have, so we have previously calculated what is the value of the delta, right? So the value of the delta, it is going to be, you're just going to have this, and then you would have like the standard normal, which is, which is going to be like a cumulative function, right? And then D1, right? So basically, sometimes they can the has like 1,000 normal D1. So you just need to find what that D1 is. So you are just going to substitute these values over here. So you can see that the stock price is 20 Rand. So you can see that ST is 20. The risk-free annual interest rate R is going to be 0.5. the volatility is going to be 0.3. The strike price K is going to be like 25, and maturity T minus small t is going to be like 1/2. So you are just going to substitute these values into your D and then find what that value is. Is there any question? Tristan, do you have any question? And then how about you, Chapelo? Is there any question from your side? Is there something that I need to explain some more? Okay, so I think we can end here. Is it fine with everyone? Do you guys have any questions? Is there any concern, any feedback? Do you want me to re-explain some other concept that you didn't understand before? I can do that, by the way. We still have time. So you can ask me any question from all the way to bonds and interest rate, Feynman-Kac, the stochastic derivative of differential equation. So you can just unmute your mic, and then you can let me know. So, and I'm going to stop recording, by the way. So. Okay, then thank you. I think this is it for today. And thank you for attending. Enjoy your week and your semester test as well.